A couple of last things to look at. Ideas when integrating. We've looked at some of these ideas before about the symmetry of the function that we're integrating. So remember, even functions, we know they have symmetry in the y-axis. So function negative x equals function x. And so if instead of integrating from negative a to a, we could go twice from 0 to a. Sometimes we do that just because 0's an easier number to substitute in. But of course we can still use the idea if we notice that we've had an even function which has been shifted horizontally. So say it's shifted over to some point C, and then we notice the symmetry about the point C. So we're going to C plus A and C minus A. So we see the same amount either side of that midpoint. Then we could go 2 from C to C plus A. And probably substituting the C in will be easier because of the x minus C part of the function. That'll probably turn into 0 and have a similar effect. It may never happen, but it's just something to keep an eye out for. You never know. Could come in handy. And a similar thing would happen with odd functions, of course. Reminder, odd functions, that's function negative x is equal to negative function x. And so in this case, if we're doing an integral rather than finding areas, remember the bit below will cancel out the bit above because of symmetry. The integral will always be 0. So that's probably a more useful one if we noticed a shift. Because if we do notice it's an odd function that's been shifted and we see the symmetry about that point where it's been shifted to, again, we can just say, oh, well, that integral would be 0. And that can save us a bit of time if it is something we notice. A third one. This is an interesting relationship. If you integrate from 0 to a of function x, you'll get the same answer as if you integrate from 0 to a of function a minus x. Okay? It'll come up with the same result. Now, let's just prove that. A very simple thing to prove. There's function a minus x. If I do a substitution, u equals a minus x. So the du just becomes minus dx. And we'll change our limits. So u is a minus x. So when x equals 0, u is a. X equals a, u is 0. And then we end up with minus the integral from a to 0 of function u to u. But remember, we can get rid of that negative sign by swapping the limits around. And so that would be the same as the integral from 0 to a of function u to u. So thus, I mean, u, when we're doing a definite integral, it doesn't matter what the pronumeral is because we're going to be substituting in anyway. So that would be the same as function x dx. Keep in mind when we're looking at odd and even functions, odd times odd will give us an even function, odd times even will give us an odd function, even times even. So if it's the same type of function, it'll give you an even function. Different type of function, it'll give you an odd function. So something like this then becomes quite easy. See, now that we've seen all these different techniques, you might look at this and go, sine cubed x. Okay, I'll extract out the sine x or the sine square, however you're going to approach this particular problem. But the first thing, if you do notice it, we've got the symmetry about the origin, and sine, remember, is an odd function. Now we've got an odd function cubed. So it's odd times odd times odd. Well, odd times odd, that'll give me an even function. But then multiply it by an odd, the whole thing is an odd function. So I've got symmetry from -1 to 1 of an odd function. Well, that's just going to be 0. I don't have to worry about using my techniques of sine cubed and so on. So it's a nice little question to throw in to see who's paying attention, who spends a lot of time working out the sine cubed. I mean, of course, it'll come up with the same answer as 0, but you can save yourself a lot of time if you notice the symmetry. X squared root 1 minus x. This is where that idea of the a minus x, function x being the same as function a minus x, comes in handy. Because this I can't expand out. I've got 1 minus x to the power of a half. But the power of a half, how do you expand that out? But if I change it, everywhere I see an x, I'm going to change it to 1 minus x. Remember, the integral was 0 to a, and we replace it with a minus x. Then it becomes 1 minus x all squared, which I can expand out, times the square root of x, and then I've got something I can just simply add 1 to the power over the power 2. So integrate that, subbing in 1, subbing in 0, we get our answer. So again, that saved me on using some sort of, if I didn't do that, I'm going to have to do some sort of substitution or, integral to get rid of the square root. A lot less work by noticing that. So if you have 0 to a, you can always substitute in a minus x. All right, improper integrals. Now this is an integral where we're actually integrating over something that's undefined. So let's have a look. Something like this. There's a hyperbola. And I want to integrate from 0 to 1. But clearly, we can see our picture of the hyperbola over there. It doesn't exist at 0. So how on earth do you integrate something like this? Well, that's where we use limits, because we know it can't actually be 0. But as it's approaching 0, we can have a look at it. So the question really becomes, all right, I'm going to change it. I'm not going to say it's 0. I just want to know what the limit as n approaches 0, the integral from n to 1 will be. Because I can integrate dx on x. Obviously, we get log x. So it's the limit as n approaches of 0 log x when we substitute in 1 and substitute in n. So minus log n, well, that's still undefined, because if I now substitute in 0, well, log of 0 is undefined. So that one stays as undefined. That integral cannot be worked out. But there are others which can. 1 to infinity of xe to the x squared. So you have an infinite area, you would think, because it's just going to keep going and keep going and keep going and so on. So again, we'll do it the same sort of way. I'll integrate from 1 to n and say, well, we're going to find the limit as n approaches infinity. And xe to the minus x squared, that's something I can integrate. Be minus a half e to the minus x squared, subbing in n and subbing in 0. Now, the limit as n approaches infinity of e to the minus n squared. Well, that does have a limit. Because if you think of the curve e to the minus n squared, that limit approaches 0. And so the answer is just 1 on 2e. Because the e to the minus n squared will approach 0. So whilst you would think, oh, surely it has an infinite area under this curve because it just keeps going. Well, actually, no, it has a definite area. It's very much like what we saw with sum to infinity with sums. And you think, oh, well, surely if we just keep adding, the sum must be infinity. But it turns out sum to infinity is not infinity. And it's all to do, in that case, with the sum to infinity of what the ratio is. In this case, it's to do with convergence. So, all right, now let's have a look at another idea. Area and inequalities. So if I know that a function is in between two other functions, so if I was to draw all three pictures from A to B, and the g function is always below the f function, is always below the h function, then their integrals will also be in that order, so the value of the integrals. And if you think about it, that makes sense, because if you draw a picture, then clearly the area under the lower curve will be less than the area under the middle curve, will be less than the area under the top curve. So here's an HSC question from, well, not that long ago, 2009. So here's the graph they gave us. It's y equals 1 on x. N's going to be a positive integer greater than 1. So they've told us the area of the region from n minus 1 to n, there it is. And we're going to estimate it by areas between rectangles, and they've drawn in two rectangles there. So we want to show this lovely expression, e to the power of n on n minus 1 is is less than 1 minus 1 to n to the power of n, which in itself is less than e to the minus 1. So all right, they want me to use the idea of areas, so I'm going to say, well, I know the area of the inner or the smaller rectangle must be less than the area under the curve itself, which must be less than the area of the outer rectangle, the one that went outside. Well, the inner rectangle, the width was 1, or the height was 1. No, the width was 1. And the height was function n, so 1 on n for the height, which is less than the area under the curve, so that's my integral from n minus 1 to n of dx on x, is less than the outer rectangle, which also had a width of 1, but a height of function n minus 1, so we get 1 on n minus 1. Tidying that up, I now have this expression, and integrating at the same time, so my dx on x, integrate it became log x. substituting in, you notice with the log function, I often do this. I don't worry about writing log minus log, because I just go straight to my log law and put it into one fraction, because it's always going to have the same coefficient, of course, because we're substituting into log each time. So I've gone straight to the log of the top one divided by the bottom one, because I would have had log n minus 1, bring it all in with a log law. Okay, well, let's get closer. Well, I'm going to multiply everything by n first of all. And you get 1 is less than n lots, and then I have the n on the n minus 1. Then I'm going to bring the n into the log. So I now have n on n minus 1 to the power of n. Now, we know e to the power of x is continually increasing. So therefore, e to the power of 1 must be less than e to the power of log, that expression, is less than e to the power of n, e to the n minus 1, because they're bigger numbers as we're going along. We've just said that 1 is less than that, therefore e to the power of 1 must be less than that, because e is always increasing. Now, I've turned everything upside down. So my inequality signs have changed. Well, that's the one we often forget about with inequalities. We always remember that, hey, multiply and divide by a negative number, change the inequality sign. But the other condition was, if you turn both sides upside down, you change the inequality sign as well. So I've turned everything upside down, so my inequality signs have changed. Looks a bit strange looking at it like that. So let's rewrite it the way it should look. And so I've also tidied up here. This was on the right-hand side, we had 1 over e to the n on n minus 1. So rather than having 1 over, I've made it a negative indice. So you've got e to the negative n on n minus 1 there. Same with the 1 on e, I changed that to e to the negative 1 as well. And the other thing I've done, n minus 1 on n, I've rewritten as 1 minus 1 on n. Because remember, I'm keeping one eye on what I'm trying to prove. And that was actually, I think, what we had to prove, wasn't it? So there we are, we're there. See, I don't know why they wrote it as negative n on n minus 1. Personally, I would have preferred n on 1 minus n, just because I don't like the negatives, but that's just me. So that's the idea of using areas, I suppose, to prove inequalities. All right, here's a handful, a big handful of questions. The 100. But of course, it would be mean giving you 100 integrals to do, so you don't have to do number